Good evening, everyone, and thank you so much for coming out tonight. Welcome to the Shoreline Change Special Area Management Plan stakeholder meeting. We have a really great speaker for you tonight that I'm sure you'll enjoy. Dr. Oppenheimer will be coming on in a few minutes, but we wanted to start out by just sharing with you a few tools that have been under development for the Beach SAMP project. And we have a couple of speakers to share with you the update on the tools, and then I'll turn the floor over to Grover Fugate, who will then introduce Dr. Oppenheimer. My name is Teresa Crean. I'm a coastal community planner here at the URI Graduate School of Oceanography Coastal Resources Center in Rhode Island Sea Grant, and I serve as a project coordinator for URI in partnership with the Rhode Island CRMC. We have a couple of tools. We have the Beach SAMP website that you're seeing up here. We've made some modifications to that website, so I just encourage you to continue to check back with our website, because we do have new tools and information emerging and being posted as it's available, and different news stories and such. So we encourage you to give us any feedback on the website that you have to make sure that we are communicating this complex material effectively to our various audiences and stakeholders across Rhode Island. The first tool that we wanted to share with you tonight is an online tool called My Coast. I'm going to ask Janet Friedman from the Rhode Island Coastal Resources Management Council to come up and share with you that tool. Okay, Janet, you have to talk into the microphone.
Oh, thank you, Teresa.
I will get your slideshow queued up.
Oh, do you have a, do I turn it off? Do I do the slide
Yes.
presentation?
Go ahead and get started.
Okay. Good evening. Now I have 5 minutes to introduce you to this tool. So this is My Coast in 5 minutes. It's a tool so that any citizen scientist can go out and you can actually map the coastal flood events, whether they're extreme astronomical tides or if they're storm events. So I have my contact information at the end, and I'd be happy to give it to you if anybody wants some more information. But this is it's a smartphone app. It's a free app. You can download it onto either your iPhone or your Android. And you have choices of different tide events, different flooding events. Just to give the credits where credit is due. This was developed by Blue Urchin, and the original funding came from NOAA, and then we have additional funding from NROC. Now, there's a national project, and the goal of this is to have every coastal state have a My Coast site. Right now, only the New England coastal states have them, as well as South Carolina. So each state develops their own site. They're all a little bit different. But in Rhode Island, the administrators are the CRMC, the URI Coastal Resources Center and Sea Grant, and Save the Bay. So you download the app, and once you put it on your smartphone, you click what kind of tide event you want. Hit the King Tide Report. You take a photo with your phone, hit Set Location, and then Add Report. And once you do that, this is the report that's generated. So here we have a King Tide Report that, again, it geolocates you from where you set your location, gives you the time and date of the photo, and it will tell you how close you were to high tide. Gives you a weather overview. So this day it was raining and a little windy, so it was a bit of a stormy day, which impacted the tides. You can get more detail on the weather by clicking this hyperlink, and then it gives you tide data. It tells you what tide station it's taking the data from, and how far that tide station is away from your location. And it will give you your water levels at the time that you took the photo, as well as the high tide that day. And if you click on the tide station, that will bring you to the tide data from that day. So in this case, the blue is the predicted tide heights, and the green is the actual tide height. So on this day, the predicted tides, the predicted astronomical tides, were already going to be more than a foot higher than mean higher high water, or the average high tide. But because it was rainy and a little stormy, the tides were actually about a foot higher than that. So on this day, the tides were about 2.5 feet higher than what the average high tide at this location was. And thus you had flooding. Now, if you don't have a smartphone, don't worry. You can also submit your reports on the mycoast.org website, so it's www.mycoast.org. And on the website, there's a lot of on the website, you have information. It will give you a schedule on when you're going to have those astronomical high tides. You can submit a storm reporter report or a king tide report. Now, I want to emphasize, we do not want you going out in a storm and taking pictures and submitting them. But after a storm, there's a lot of evidence of how high the water was, how far it's flooded inland, and a lot of the damages. So go out the day after and then submit your pictures. And you can look at reports that have been submitted either geographically or later you can see that you can search them under the different tabs. So this is the king tide tab. It's just a non-scientific word to indicate that these are the astronomical high tides. They're the extreme high tides. And we define these in Rhode Island as any tide that's at least a foot higher than mean high water. So you can add your report, you can search reports, or you could look at the photos there. Under the storm reporter, and again, I want to emphasize, do not go out during the storm to take photos. So you can, again, search these reports, or you can retroactively add your report on the mycoast.org site. So just add a storm report. You'll get, one of the things that you have to do if you add your storm report is you'll have to locate it yourself on the map. But again, you get the same information, but there's also a damage report that comes with this. And I think it's fairly simple and intuitive, but you know, that's me. So we will be having a storm reporter training session at Save the Bay on May 31st. And I think you can go to the Save the Bay site. They will have more information on that if you're interested. And we'll go through the reports and what to look at. Another feature that's really kind of interesting is under the Rhode Island MyCoast tab, there's a tab that says live streaming, and what this is, as reports are coming in, you're going to be able to see them all. So this is a big interest to, I know the National Weather Service has used this so they can fine-tune their coastal flood warnings, but also we're talking to some of the EMA on how they might be able to use this, and I know of at least one TV news channel that's very interested in this feature. So, later this week, we are going to be having some king tides, the extreme astronomical tides. So, May 5th and 6th should be good days for taking photos. The 7th and 8th, it's late, so definitely on the 8th it's going to be too dark, but the 7th you might be able to get some shots. Now, if it's just an astronomical tide, you'll probably have some flooding in the low-lying areas, but if it's stormy at all, you could have more significant flooding. So we'll see. And just to show you how we are using this, as I said before, the National Weather Service has used these to look at their coastal warning system, but then municipalities can use them to identify places that are susceptible to flooding and do immediate road closures or look at long-term planning. So to see if they want to relocate some of these roads. It's also being used to verify, we've looked at them to verify the storm tools sea level rise modeling, and I have to say the storm tools are right on. And then it's also good to visualize the impacts of future sea level rise. And we can't be everywhere at once, so we hope that all of you will go out and download this tool and go to different areas and take some pictures at high tide. And here is my contact information. It's jfreedman@crmc.ri.gov, and you can just go to the CRMC website and you can contact me there. So, thank you.
Great. Thank you, Janet. Next up, I'm going to invite Emily Petrolia to come up and share with us a new map, something that's called a map journal. It's an addition onto storm tools to take us through a history of some Rhode Island storms.
Thank you.
You don't need that, right?
Oh no, I'll just be using my hands. But also thank you, Janet. And MyCoast is really helpful for me because I'm working on some of the sea level rise visualizations. So thank you in advance for your participation in that. So I'd like to tell everybody today about our new mapping app, which is Touring Historic Storms in Rhode Island. It's just one of many apps that we can make with the wonderful Storm Tools product that we have. And so you can find this on the Beach Stamp website or in ArcGIS online. The goal is to sort of let users go through a tour of what storms in the past have caused in Rhode Island. We picked 4 storms that were that really affected us in the past and that we have in living memory. There's the Great New England Hurricane of 1938. We did 1954 Carol, Hurricane Bob in 91, and of course, Superstorm Sandy. So on our front page, we just have instructions, and you can see our map of the state there. And then as you scroll down, you can click on any of these side buttons or scroll. You get an introduction to each hurricane as you go through, and you just see the path of the hurricane, where it sort of made landfall, and some information about it, the impact that it had, the wind speed, etc. And then we take you into zoomed-in places where we have these great historic photos of the impacts that these storms cause. So you can see these 2 photos in downtown Providence. And if you click anywhere in the map, you should be able to. Usually you can. This is very sometimes typical of ArcGIS Online. But if you click it, normally it will give you a pop-up showing the estimated flood depth at that particular area in that storm, which I think is really interesting and fun to play around with. So we've got these great photos that show just, the kind of thing we experienced with these storms and where they are on the map. And then introduce Hurricane Carol here, which was a Category 3 storm. And then you can see, I really love this photo because you can really see the end of Winnipock there and the sand. Hurricane Bob, 1991, which many of us remember. And it will load in a second. But it was I think it was only a Cat 1 when it hit us and still caused a lot of flooding. So it's really helpful to see, in the past we've had these hurricanes or tropical storms come through Rhode Island and cause some damage. And then of course Superstorm Sandy wasn't even a hurricane by the time it reached us. And many of us recall the damage that was caused by Superstorm Sandy. Apologies for the slow internet tonight. But anyway, you can imagine these are on the map. Many of us remember these photos and the devastation that Sandy caused. And now we're back. And then the other thing is at any point there's links to click into another map that allows you to look at all the different storm scenarios, but you can look at a property that you care about, your home or somewhere else. So you can type in an address here. So you can look at a generic 100-year event or each of the hurricanes that we just went through. So I'll type in an address I lived at last year. Well, again, maybe the internet's being a little funky today. But anyway, you can look at an address, say, now I live on Great Island, so say you're on Great Island, and then you can go through the different storms and see the flood extents and the depths where you were there. And I recommend trying this at home. It's really fun, and it works a little better when you're not on the internet, everyone's sharing at once. So anyway, thank you.
Thank you, Emily. There is a link directly to this map viewer on the Beach SAMP website, both on the home page and also on the Storm Tools page. So we'll be formatting more maps in this fashion to make it more user-friendly and accessible to a wider audience. Dennis, I did learn that the projection system in this room is not functional this evening. We understand there is a master plan process for Bay Campus. We've asked for plug and play new AV, so hopefully we'll get that at some point. So thank you, Emily, and I'm going to turn the floor over now to Brian Oakley, who's going to walk us through some advances in shoreline change mapping. Brian.
All right, thank you, Teresa. Those of you that are at the February stakeholder meeting all just collectively went, oh, this guy again. I'll be brief tonight. I have to project. Okay, I can't wave the mic around and I have to project. Okay, got it. So I was having a panic about what Emily just went through, so instead of going on to the web mapper in ArcGIS Online, I decided I'm going to just show you some slides of what it would look like if I was online. I know everybody's busily downloading the MyCoast app right this second, and that's why the wireless is slow on campus. So one of the things we're going to do, and if you're at the last stakeholder meeting, we talked about the static PDF versions of the shoreline change maps, and I pointed you to two different sites. You can get at these both through the CRMC website, because these are, of course, a regulatory document. They went up to the Secretary of State's office. The council approved them last week, and within 20 days, they should be the official shoreline change documents for Washington County. You could also get at them from the Beach SAMP website, beachsamp.org, under the tools, or now it's Understand Risk tab. One of the other things we wanted to do is to get away from, well, these static maps are great for people who want to download a PDF and look at their particular site. They're not as user-friendly for people who either want to explore and look at the shoreline that they go to, they visit, or perhaps even they're looking at property along. So we've been working away from the static maps, or working in conjunction with that, to make a web mapper, where essentially you can have all the same information in a more accessible format, again, through ArcGIS Online. Excuse me. So instead of having to go download a PDF or 45 PDFs, if you wanted all of the maps, you can go to the web mapper and get exactly the same information. Now, I will, Janet had her caveats about not going out in storms. If you're doing this for a permit, go to the CRMC website and get the official map document. But if you just want to look at shoreline change in an area, this web mapper is where you should be headed just to explore the data. So one of the things you will notice, and it doesn't work for me anymore because I've logged into this a number of times, but your very first time logging in, words to this effect come up with a little, yes, I have read this document, which, having surfed the web and downloaded programs, I've never once actually read what I'm supposed to read. I always just click agree. I encourage you to actually read this, because it not only explains how we do the shoreline change maps, but also reminds you that when we're talking about shoreline change, we're looking at something that's happening over a long time scale, say measuring shorelines from 1939 to 2014, and incorporated in that are storm events that are happening very rapidly. So in a storm like Sandy, in a place like Matunic, we measured 8 or 9 meters of bluff retreat. Okay? And that gets factored into this long-term shoreline change. So always keep in mind, while we present annualized rates, erosion doesn't work in an annualized fashion. It's storm-driven. Okay? So as we get into this, it looks like a lot of the other web mappers, if you're familiar with ArcGIS. If not, it's a great software package or online package. You don't have to have any special training. Okay? If you click up here, you can change things like your explanation box will pop up. And since you can't read it, it looks something like that. And this is a very simple map viewer. It's got your shoreline positions from 1939 to 2014. They're color-coded. And there's also these lines that are perpendicular to the shoreline. If I zoom in on them right in here, okay, that we call transects. And these transects are the actual spaces where we measure shoreline change. So I've selected one here on the Charlestown Barrier. And as you select it, what pops up? You can't read that. Let's zoom in. You can get a total change of 140 feet between 1939 and 2014. And that annualizes a rate of just under 2 feet per year, kind of average for a chunk of the South Shore. So on all 1,900 and something transects for Washington County, excluding Block Island, we're working on Block Island, hopefully next year, you can get this information. We also added a tool in here, just like a lot of the other web mappers. So I put Matunic in because everybody always asks about Matunic, and that right there, in case you're wondering, is 90 meters of shoreline change between 1951 and 2014. Just always keep that in mind when you're thinking about coastal processes in Matunic. We also added a tool where you can actually search by address, just like on all the other web mappers, storm tools included. So I went to one of the sites of our long-term beach profiling measurement system that John Boothright started in the 1970s, 808 Charleston Beach Road, and it takes you right to it. You can zoom in there, okay? And it takes you right to the transect you want to look at. So if you live along the South Shore, you're looking at a property along the South Shore, you can go and find that in about 30 seconds. You go to the Beach SAMP website. This will be live shortly. I'm hoping within a couple weeks. Type in the address. It'll take you right to your transect, and you can get your shoreline change numbers that fast. That's what I got. Any other questions? It's about the shortest talk I think I've ever given for the Beach SAMP.
Great. Thank you, Brian. We will have time at the end for questions, whether for our speaker or for any of us on these tools. We'll be bringing more of this to you in the coming months. So I'd like to now ask Grover Fugate to come up and take the mic and introduce our guest speaker.
Thank you. Thank you very much. Can everybody hear me? Yes. Okay, great. We're really fortunate tonight, and the council's very pleased to, in association with our partners here, have this presentation tonight. In fact, our council members, there are actually quite a few here tonight. We have Mike Hudner, Paul Lamont, Paul Beaudet, Don Gomez, and Ann Livingston, our chair. Paul Lamont is our vice chair. They're all here tonight to actually hear this talk. Tonight we're going to hear from Dr. Michael Oppenheimer. Michael is one of the world's leading experts in this particular area. He is a professor at the geosciences at Princeton, and he has been a longtime member of the International Panel on Climate Change and one of the lead authors of that report. Michael's CV, I could sit here and spend the next 20 minutes going through it, but he is a very, very accomplished person. He is extremely well known for this. Tonight he's going to be talking about climate change and in particular sea level rise. And he's actually going to bring some of this down to the Rhode Island shoreline so that you can start to see how this all fits in. Without any further ado, I want to let our guest have the majority of the time here tonight. And again, thank you very much. We are very fortunate. Thank you.
Yes, thank you.
So, thank you, Grover. If people can't hear me in the back as I go on, please signal and let me know. It's always a pleasure to be here. I spent a lot of time on Block Island, and I have friends in Providence, and I always love to come here. You know the expression, think global, act local. Well, if there was ever a case where that comes down to the point, it's here, coming here, talking to the people on Grover's staff, hearing how they approach this not just looming, but manifest problem of dealing with coastal risk gives me hope, actually, that something sensible will be done. I come from a much larger place. I actually live in New York City, and I am a participant in the decision-making process. I'm on an advisory committee the mayor set up, and for all the great resources that New York has, it does a fairly good job also. But in terms of really grappling with the technical aspects of the problem, you do as good a job here as they do there. So with fewer resources, I'm sure. And I also want to thank Grover and Mike Kuttner for reminding me what the punchline on my talk is, so I'll give it up front, which is that the basic problem is that the risk on the coast is changing and changing fast, and it's going to change in radical ways. And we're not even very good at dealing with the level of risk we have today. So we have to up our game and up our game quickly because the world is changing literally as we speak, and the sea level is rising. There's a good chance that storms, coastal storms, particularly tropical storms, are going to be intensifying, and then if we get on it, we're just never going to be able to catch up. And that'll be a burden, not so much on us, although it's already a burden, but on our children. This is what happened. The whole take on coastal risk was changed, at least for the time being, by Hurricane Sandy. That's an iconic picture. The trouble is that these storms, well, it's both good and bad. These storms don't come very frequently, which is a good thing. They'll be coming more frequently in the future, which is a bad thing. And the difficulty is our memories are very short, and we don't retain the information, and in particular, we don't retain the impact as a body politic, which we will need to do. So let me talk a little bit about the scientific details on the problem, and then I'll go on and talk about the framework for actually approaching a solution. So here we have 3 panels. This is the global average sea level rise over the past century, and it's been up, up, up. We know this originally from what are called tide gauges, the little flotation devices that the National Oceanographic and Atmospheric Administration maintains. If you go out on the coast, you can stumble on one every once in a while. At least you stumble on a brass plaque in the ground, which indicates there's one off the coast. And they measured sea level for over 100 years. There was a good network in place. And then the red curve is the measurements from satellites, which gave a truly global picture of the height of the sea level. And this was important because the tide gauges were mostly along coastal areas. And you notice that there's a good overlap between the satellite data and the tide gauges, so we have good high level of confidence that these numbers are correct. And also, in both cases, the signal is accelerating. The signal is growing. The rate of sea level rise has increased by something like 50% over the last 20 years or so, and that's because the basic sources, the causes of sea level rise, which I'll talk about in a moment, have accelerated. And to put this all in context, this is, you don't have to worry about the numbers, this is in millimeters per year, which probably doesn't mean much to you, just put it aside for a second. Over the past 20 years in the satellite era, the sea level rise rate is about 50%, a little more than that, bigger than over the average for the 20th century. This average is for 20th century, satellite era. And before that, using indirect evidence of what the sea level was, which are basically notches in ancient coral reefs, because coral reefs try to grow up to the level to stay a meter or so below the sea level. The levels, the mark of the sea on old coral reefs as the sea rises and falls tells you where sea level was a long time ago, as does evidence of changes on ancient beaches. Those give you marks of where the tide line was. When you sediment records, when you put all that together, you get this, about a tenth the size of the sea level rise in the 20th century, and even less than the sea level rise in the recent era. So we are quite confident that sea level rise has been accelerating. We also have good evidence that that is tied directly to the warming of the Earth due to the buildup of the greenhouse gases. Now, Earth is projected to warm if we do nothing about it over the next century by somewhere between about another a degree Fahrenheit and something over 10 degrees Fahrenheit. A degree Fahrenheit we could probably manage fairly well in terms of adapting along the coast as well. 10 degrees Fahrenheit would be unmanageable and, according to most of my colleagues, disastrous. I won't go into the various details about climate change tonight, but I will show you the resulting sea level curves. There are 2 worlds here, the orange world and the purple world. The orange world is basically, let's not worry about climate change. Let's not worry about the buildup of carbon dioxide and other greenhouse gases. Let's just party. Let's just do what we would have done anyway. Let's pay no attention to it. And if that's possible, which it probably isn't, we would see an upward curving rate of sea level rise, so that sea level by the end of this century could, within the uncertainties, which is why there's a band here, wind up as much as a meter, more than 3 feet above current sea level. By the way, if you think 3 feet, we could live with it. On a typical East Coast beach, depending on where the beach is, there are different estimates about how much land that would take away by submergence and erosion. And the numbers range. There's a kind of an old rule of thumb says multiply the vertical rise by 100. There's a more recent value for some beaches around here I heard today where they use a value of 30. On the other hand, some of the south-facing beaches look to me like they were regressing at a rate of about a multiplier of about 300. So it means you're talking for a sea level rise of 3 feet, somewhere in the range of 100 to 1,000 feet of losing beach inland, depending on what beach you're actually sitting on. And that's just the beginning. We have, of course, the vulnerability of infrastructure and populations, because during storms, if the sea level is higher, that means the flood level is higher. And the surge is going to push inland to places it never got before. So those are the basic risks from sea level rise. And if we act to stem the increase in the emissions of the greenhouse gases, and there is some evidence that that is happening. Last year, for the first time in a period of global GDP growth, carbon dioxide emissions actually declined slightly. It was a complete surprise, and we're not sure whether it was a temporary glitch due to the slowdown of the Chinese economy, or whether it reflects longer-term trends, such as the penetration of more natural gas into the energy system, displacing coal, and the revolution that's occurring in the price of renewable energy, which has allowed solar energy and wind energy to really penetrate the electricity system globally for the first time in a significant way. But if we do that, we get the purple area. A much lower sea level rise could be as low as 30 centimeters down here, something around a foot. But still, you notice there's the march upward of sea level in either world throughout this century. And you also notice that regardless of what decisions we make on emissions, until about 2050, the future is baked in anyway. So we had better be prepared to deal with sea level rise, because no matter what we do, no matter how effective we are at cutting the greenhouse gas emissions, we are going to get a substantial amount of sea level rise by 2050. So why is this happening? There are 3 fundamental reasons why global sea level rise is occurring. One is that most liquids expand when you heat them. So we're heating the oceans. Earth's temperature, the atmospheric temperature is already about more than 1.5 degrees Fahrenheit warmer than it was a century ago. That's penetrating into the ocean and causing the ocean to expand, takes up more volume. That's obvious. In addition, ice is melting all over the place. In particular, mountain glaciers are shrinking. Probably by the year 2200 or so, almost all mountain glaciers will be gone if the business as usual projection, the party projection, plays out. And that's adding water to the ocean. Most important of all in the long term is that we have 2 great ice sheets remaining on Earth, one around the poles, one in Antarctica and one in Greenland. They hold a lot of ice, as I'll show you later, and they are both, at this point, gradually, slowly shriveling away. And all of that is adding mass to the ocean and causing sea level to rise along with the volume expansion. We have a lot. I'm going to show you projections of what the ocean, I already showed you a global projection. I'm going to show you some local projections of what sea level rise will do. But it's important to remember that, as I said, we don't know exactly what our future greenhouse gas emissions are going to be. So these projections are reliable maybe for the next 40 years or so, probably not so much beyond. Secondly, there are great differences between what's going to happen here, let's say at the Newport tide gauge, and what's going to happen on the west coast of the United States, and what's going to happen in Shanghai. Sea level rise is different at every point on Earth. And the subtleties of calculating how much different it is and what the exact numbers are, it's very complicated stuff, and it drives scientists crazy, basically. This is the part I spend most of my life on these days. The ice sheet contribution in particular is very difficult to produce what's called a model of. You need a numerical model to put on a computer to be able to ask the computer what-if questions. What if the world warms by another degree or 2 Fahrenheit versus 5 or 6 degrees? How much do the ice sheets disintegrate? Very hard question to answer. I'll talk a little bit about why. And finally, probably the most perplexing part of the problem is what's called exposure and vulnerability. It's how many people are going to be living in the coastal zone. Under what conditions will they be living? Will they be living in residences, working in buildings and factories that are resilient to climate change, resistant to a coastal storm, say? Or will we forget about that part of it? We'll just say, we'll worry about it when it happens, and then you get people dying, as happened in Hurricane Sandy. So how we will respond, what decisions will be made, and how well those will be implemented by the people, by the governments, that's really the most critical part of the problem at all. And again, I'll get back to the bottom line message. Because we are not so great at dealing with the current level of risk, we can't be that optimistic about how we're going to deal with the increasing level of risk unless we're really able to focus on this at this point and not put it off for another 10 years, say, or until there's another big storm. And this problem gives decision makers like Grover fits, because I have to say the information from the scientists is, it's changing all the time. It's difficult. There's a lot of uncertainty. I'm a scientist, we don't like to lie. We don't like to sugarcoat. We don't like to give you numbers that we think are false. We try to tell you what we think we know and what we think we don't know. And with this problem, it's proved maddening. These are 5 different reports from the Intergovernmental Panel on Climate Change since 1990. Here was the last one in 2014. I was an author of one form or another on all of those reports. And you'll notice that we, in the beginning, this is the range of projected sea level rise. Again, focus on the bars, not the numbers. Very wide range originally. Then the range shrunk, and the range shrunk. We thought we were getting smarter. And then it shrunk like this, and the mean went down. So we thought sea level rise was going to be less, in fact, than we now think. So we thought we were getting smarter, more accurate, more precise, but in fact, in some sense, we were getting stupider. And in the most recent assessment, it's up here. Both the range is increased again, and the mean is about double what we thought last time. It doesn't really mean we're getting stupider. It just means you have to understand science doesn't move uniformly forward from a relative state of ignorance to perfect knowledge. It's a bumpy road. And that's fine, and it makes life fun. That's one reason I love being a scientist. But when you have to turn that into a decision, which involves spending billions of dollars potentially, for the decision maker, it's not so much fun. So I have some sympathy for you people, I have to say. This is a too complicated slide, but what it basically is these are the different sources of sea level rise. There are the 3 I talked about before, which give you the big global picture: mountain glaciers, thermal expansion of ocean water, melting of the ice sheets. But then there are demons involved in each of them, which I will explain a couple of things right now, just by way of example. And it's these things in red that make the sea level rise at every local point on Earth different from the global average. So that the rate of sea level rise now here, say at the Newport tide gauge, is about 50% higher than the global average. Turns out this part of the world got unlucky. It got unlucky because the dynamics of the Gulf Stream happen to mean there's a pileup of essentially warm water in our neighborhood, which means we get more sea level rise. Also, strangely, Earth's crust is still rebounding from the loss of the big Laurentide ice sheet, which covered much of the northeast United States up to 10,000 years ago. And as the Earth slowly regains its spheroidal shape after the loss of that big mass of ice, the ocean bottom changes, the coast changes, and the net effect around here is the coast is sinking relative to the ocean bottom, and that effect is effectively pushing the sea surface up too. So we're kind of running with a headwind. Even if we got global warming solved, there'd be a little bit of sea level rise anyway. That effect is added on to the amount we're getting due to global warming. And then there's another cute effect I'll talk about. Turns out these ice sheets are so big, they're so massive, that they actually attract a significant amount of ocean water to them. So if you looked from space with the right device, you would see a big bulge of ocean water, like a donut, surrounding the Greenland ice sheet, and a similar donut surrounding the Antarctic ice sheet. And when those ice sheets melt, or I should say as they melt and get less massive, the gravitational attraction that they have for that water decreases. So the donut starts to expand, get a bigger radius, and the water starts to diffuse around the ocean. So the effect of losing water, losing ice from one of those ice sheets, is not only do you increase sea level rise globally, but you also reconfigure the shape of the ocean surface so that at some areas, far from the ice sheet, all this water is traveling to those areas from the donut. And in other areas, right around the ice sheet, the donut or the bulge is disappearing, so sea level is actually falling a little bit. So it gives you a very complicated pattern of sea level rise, which is different at every place on Earth. Then when you add on top of that tectonic activity, sediment changes, for instance, in every area, and some other factors, it's a damn hard calculation to do. This is a graph which shows you, this is the effect of the Antarctic ice sheet. If it lost enough ice so that global sea level went up by 1 meter, the blue areas are areas where sea level would fall. And the red and orange and yellow areas are areas where it would rise. So you get a very uneven pattern, and you get a flipped pattern from the Greenland ice sheet, because Greenland is here. It's up north. This is Antarctica. And Greenland, you get the blue pattern up north, where sea level falls in the far north and rises at great distance as that donut diffuses around the ocean. Well, in reality, we don't know exactly how much ice we're going to lose from here on what rate, or how much ice we're going to lose from here. So predicting what sea level is going to do involves not just adding up the amount of ice we're going to lose, but calculating how this gravitational response and other similar complications are going to play out over time. Again, a difficult chore. So how does this play out around here? I did a study with a bunch of colleagues at Princeton and other universities on the East Coast, looking at 4 areas: Norfolk, Narragansett Bay, Norfolk, Atlantic City, and Jamaica Bay in South Queens in New York City. And we studied the rate of sea level rise, we projected sea level rise, we projected future storm surge from our knowledge of the frequency of storm incidents, and we actually worked with some engineers and architects to make tentative sort of proposed plans for how you deal with the amount of sea level rise that we expect. And in the process of that, we looked at the rates of sea level rise. You know, Norfolk really has a very high rate of sea level rise, 4.3 millimeters per year. Sustained over the last century, but look, the curve starts accelerating up here, just like the global curve as shown in that satellite data. Same with Narragansett Bay, 2.7 millimeters per year, but the curve starts swinging up. That upswing is probably due largely to the accelerated loss of ice in Greenland and Antarctica, and there's the global mean showing more or less the same behavior. So we then calculated, using this limited modeling capacity that we have at this time, due to this problem of not being able to accurately model the ice sheets, what would happen in the future. So this is the average, the median, the most likely guess for New York, Newport, Atlantic City, and Norfolk. And we see in the party scenario, we're just going to ignore this and let it go, no policies aimed at cutting the greenhouse gases. That's what this means, RCP 8.5. We see a sea level, this is in centimeters, so about a meter, which is 3 feet basically, in New York, Newport, a little more in Atlantic City, and also in Norfolk, for a global average of about 0.8 meters, or about 2.5 feet. But there's a 5%, that we do what's called the confidence intervals. There's 5% chance the sea level rise is less than these numbers, and there's a 5% chance that it's above these numbers. So the 5% confidence limit for New York City or for Newport is basically 1.5 meters or more than 4.5 feet. 4.5 feet is a huge amount of sea level rise, and my own view is we're in a position to be able to deal effectively with a foot or two of sea level rise, but 4.5 feet is a totally different world, so we have to hope we don't get there. And this is a projection for the that we made of what specifically is we expect to happen at Newport. There's a 66% chance that sea level rise is in here by the end of the century, again in the party scenario, winding up around a little short of, right around 3 feet. But there's a 17% chance it could be as much as about 1.33 feet, about a 5% chance that it gets 1.2 feet, and about a 1% chance that it gets to 2 feet. I'm sorry, these are meters. I'm sorry. 6 feet, 4.5 feet, 4 feet, 3 feet. And you have to decide, I mean, maybe you don't personally want to decide, your decision makers have to think about which risk they're going to manage for. And as I said, these numbers are kind of loosey-goosey because we don't know exactly what emissions are going to do, but these numbers are more serious. And we're talking about sea level rise in Newport of something like 0.5 meter by the middle of this century, or about, 1.5 feet, and that's right at the edge, in my view, of what we know how to deal with effectively right now, and I'm not even so sure about that. So what is the difficulty in making good estimates here? Well, it's, again, that we have a difficulty creating good computer models of the ice sheets. Greenland contains enough ice so that if it all melted, we get 7 meters of sea level rise, around 23 feet. Luckily, that's a slow process. It's melting slowly. It's going to contribute several tens of centimeters, maybe something on the order of 1 foot or so this century. The western part of Antarctica is based on bedrock, which is below sea level. And because it's below sea level, the ice sheet has the potential to what's called go unstable and essentially float off its base. And that can happen very quickly in geologic time. This would disappear over the course of a few thousand years if we kept cooking it, a gradual slow rate. This could disappear in the course of a few hundred. That would be a very high rate of sea level rise. And then on top of that, there's 52 meters, or about 170 feet of sea level rise equivalent bound up in East Antarctica. That's huge. We'd all be running if that were really about to happen. It's not, because most of East Antarctica is believed to be impervious to a warming unless it gets in the neighborhood of about 15 or 20 degrees Fahrenheit. And although that's theoretically possible if we burnt all the coal and oil, I think human beings aren't that stupid. They're not going to party for that long. That's my view. But there are areas around the edge here which also are bedded below sea level, like West Antarctica. So the total risk, when you add together the ice totally that I think could go over the long term, you're talking about something like 10 or 15 meters here, another 7 there. You're talking 50 or 60 feet of sea level rise. That's what we're really exposed to. And if you ask how much of that could really go fast, we're talking probably about 5 to 10 meters. And by fast, I mean a few hundred years. And I'll tell you one reason we think that is the last time Earth was about 4 degrees Fahrenheit warmer than today, which is about how warm we think it'll get by middle to end of this century in the medium scenarios. Sea level was 5 to 10 meters higher than today. The way we know that is we look at these ancient coral reefs. Remember, I told you coral reefs grow up to be near the sea surface. So when the sea level rises, these coral reefs grow up, and then when the sea falls, they're exposed. So here's the period 125,000 years ago called the last interglacial, when sea level twice during that period was between 5 and 10 meters above in 2 jumps First this one, then this one, which went up to about a couple of meters higher than that one. Right here's the high point. It may have gotten above 10 meters. And so here are the two marks, or the two benches on the coral reef, marking first this sea level, and then that sea level, and then the sea fell after that and never got that high again. So it's through studies like this that we're able to estimate, and we're able to confirm our estimates that in fact we could get a couple of a large sea level rise, and the only place it could have come from basically was those two ice sheets. The thing we don't know is how fast this happened. If this happened over the course of a couple of thousand years, well, it's not nice. We would lose massive cultural amenities, things along the coast that we want to be here for future generations forever. I mean, I always think of the cathedral in Piazza San Marco in Venice, which is 1,000 years old. I wouldn't like it if that were underwater, but you'd have plenty of time to, you wouldn't be bothered by it. The future generations that come from you will have time to adjust to it. The trouble is that this could just as equally well have happened mostly from Antarctica, mostly from the fast ice loss part of Antarctica, in which case it could have played out in a couple of hundred years, and that we couldn't adapt to. That would be way too much. That would imply massive, massive dislocation. We're not going to have a clear answer for a while about how fast that occurred, but recent evidence, there's been sort of a concatenation of studies in the last couple of years, all point in the direction of a fast ice loss. It's not good. Why can't we calculate this with our fancy computer models? Well, think about an ice sheet. It's just a big lump of snow that fell in the middle of a very cold continent, either Greenland or Antarctica. And as the snow fell, it compressed. And as it compressed, it turned to ice. It's sitting there under its own gravity. Its own gravity is so big that the center of it, the mound here, squeezes the rest of it towards the edges. At the edges, it runs into the ocean. The ocean's warm, warmer than the air anyway. It's not frozen, it's right around the edge, except during the winter when you get sea ice. And so it starts to melt. Also, this pushed down the middle. Well, in the middle is at higher altitude, so it's at higher altitudes, top of a mountain, it's colder. So this is a lot warmer here than it is here. So here it's melting, and here you're accumulating snow. And over time, what happens is the center is so heavy and the edge is so thin that the ice in the center, the weight of it pushes the ice toward the edge. So ice doesn't just melt in a warming world, it also slides or slips or streams towards the ocean. And calculating melting is one thing. It's not a piece of cake, but we know how to do it. But calculating flow of ice is very, very hard for two reasons. This ice isn't like the nice ice you pull out of your refrigerator. It's dirty. It's got all kinds of crap in it that it's picked up as it grinds the stone at the base and mixes it up into the ice. So the way it moves and under terrific pressure is a very complicated problem in physics. But in addition, we have only the vaguest idea what the base looks like. So if this ice is slipping along and it's running up against a rocky intrusion on the base, it's going to run into it and stop. That slows it down. On the other hand, most of the base is actually clay-like, and it just slips over it as if it's walking on grease. And what the mixture is of bumps slowing it down and grease lubricating it, we just don't know. And our ability to indirectly figure out what's at the base, we have all kinds of ways of doing it. They set off dynamite charges on the ice and get the reflection off. You can use satellite-borne radar, but none of it is good enough to give us a real detailed perspective because features that are as small as, say, a kilometer square matter, and that's very, very hard to get a handle on. So what are we doing while all this is going on? This is my favorite city in the world, Atlantic City. The reason it's my favorite is because it's such an ugly mess, and it's such flies in your face. I hope I'm not going to insult anybody. Yes, I'm sure I'll insult somebody. This is kind of like a Donald Trump campaign speech. It's like, in your face, we don't care about sea level rise. This is This is the fact you have to deal with. And this is what we do on the coast. And this is not good, folks. We cannot do this forever because we can't afford to defend this. And it's not just a problem of the ocean coming in here, but it's the Back Bay situation. The water sneaking around from here. So, it's not just a matter of defending what's there. It's not just a matter of building smarter in the future and not putting so much exposure on the coast. It's also a matter of gradually pulling this dependence away. There are times we're going to have to retreat, and we're going to have to face that. And this is not just a U.S. problem. This is a problem all over the world, and it is not just due to climate change. This figure, these bars, show you what's called the exposure. In this case, the number of people that will be vulnerable or floodable if we get today's 100-year flood 55 years in the future when sea level is a few feet higher. China, India, Bangladesh, Vietnam, US, etc. There are three colors here. The light green color is today's exposure. How many people, this is in thousands, so this is 5 million, are exposed to the 100-year flood today. This is the change in the number of people exposed to the 100-year flood due to socioeconomic change. What that means is as the GDP on the coastal areas increases, and increases relative to the inland areas, and as people flock to the coast, and as the people are ready, they reproduce. Now, this is a bit of a cartoon because actually, if the situation is bad enough along the coast, people are going to stop streaming to the coast, one would think. There's no evidence that that actually happens, but eventually I think it would happen. And the third bar here, the third part of the bar, is the additional amount due to sea level rise and climate change. And you notice, although the climate change part is a big chunk of the bar in each case, these other segments, particularly the change, the socioeconomic, we already have a big risk, and the socioeconomic change about doubles, in this case, from China's case, the current risk. So although the climate change part is bigger than either, even without climate change, we would have a big problem. This is what I mean when I say we already have this problem. It's not just about climate change. So what do we see for the future? I've showed you some of the sea level rise numbers for the future. Now let me put that together with the risk from storms and tell you how something about the risk from floods in the future. Because sea level rise, as the sea level rises, you get a gradual erosion of the coast. You get a gradual flooding of areas that were previously more or less dry. But in addition, every time a storm comes along, as I said at the top, the water goes into areas it wasn't before. So the flood levels are higher. So a storm that used to, that say had a 2-meter flood, might have come along previously every 100 years. Now the 2-meter flood might happen every 50 years, then later 40, 30, 20, 10, and then maybe in some places before the end of the century, even every year. So I'll just show you, I don't have Newport or this area on here because we had some questions about the numbers at the last second, so I chose not to show numbers that might not be right. But this is the change between 2000 and 2100. This is for the 100-year storm, and which in the 100-year flood level is what? It's about 2 meters here? Is that about it? The 100-year mark.
Yeah, it depends on the place of the shoreline.
Give me a place, any place. Here, down Narragansett? South Shore. 2 meters, 6.5 feet, whatever. So in New York City, the 100-year flood is similar. Without sea level rise, you get that once every 100 years. But with sea level rise, in this party case, as I've been calling it, you get 9 of those occurring every 100 years. In other words, the 100-year storm becomes roughly a 10-year storm. It starts occurring every decade instead of every century. And for some places, and I imagine the situation up here might not be too much different. We have to recalculate. But for other areas like Key West, the 100-year storm occurs every other year. It occurs 48 times a century by the end of this century. San Francisco, 36 times. In Japan, 64 times. I mean, these are incredible changes. And think about how effective or not we are at dealing with coastal storms today, like a 100-year storm, and then ask yourself, what happens if that storm were occurring every few years? That's what we face if the emissions aren't restrained. But I must say, even if they are, and that's in this RCP 2.6 case, you still get some pretty awesome numbers eventually, because there's a lot of momentum in sea level rise. So this tells me we have to get much, 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 much better at coastal planning, at building resilience, at being smarter about the kind of infrastructure we site on the coast, at retreating from certain areas, and about building better in others. And that's just if the storms are the same as today. But what if the storms get more intense? There's a pretty good case that tropical cyclones, that is hurricanes in this part of the world, are going to get more intense as we move on, particularly the stronger ones. And so we did some modeling. These are 4 different climate models with which we estimate the joint effect of both higher sea level and stronger storms. And you see here, the green storm, the 500-year storm, this was done for the Battery in New York City. That's Hurricane Sandy, roughly a once in 500-year flood level. And this is the current return period for coastal storms. So the 500-year flood level has a flood height in New York City of about 2.7 meters. That's Hurricane Sandy. But now, this is the return curve once we let the storms and the sea level, the storms intensify and sea level increase as projected. And the 500-year storm, like Hurricane Sandy, starts happening every 20 years. I can tell you, as a resident of New York City, we're still not fully back on our feet. We cannot tolerate a storm like that every 20 years. It's not possible. We won't be able to deal with it. Different models have different results, but they all show this push towards big, unusual storms, like the 1,000-year storm here. All of a sudden, I don't even know what that is, but it's bad, happening, every few decades. This is not a kind of world that we want to let happen. And just to show you, so Hurricane Sandy was not by any means the worst storm that we could have had, the worst flood we could have had in New York. This is a calculation we did a few months before Hurricane Sandy hit, which coincidentally had made up a synthetic hurricane, a fake hurricane, but one that we think, given the historical data, is the worst hurricane that could hit New York in terms of flooding. And we hit accidentally right on the coast at the point roughly where Sandy hit. Sandy followed a different trajectory than this. This one came up like this. It's a lot like a storm that happened in 1821, except that one hit at low tide, Sandy hit at high tide. You notice the buildup of the red and purple in the bays up here. There's the Battery. And flood level, 4.5 meters. Much bigger than the 2.7 meter flood that we actually got. So things, even today, without global warming, could be much worse than they were. And when you add global warming on top of this, forget about it. So let's do I wish I could show you how this played out on Rhode Island. I don't have a similar dissection for the hurricane of 38, for instance, or one of the hurricanes from the 50s, but I was part of the recovery effort in that I'm on this advisory committee for the city, working in the post-Sandy period to try to figure out what went wrong and how to do it better in the future. I think this graph here tells all you need to know about, gives you a good image of why things don't work out right. This is the flood level reached at the Battery in New York for the 10 biggest storms since 1950. So it includes some hurricanes like Hurricane Donna in 1960, Tropical Storm Irene in 2011, and then finally Sandy. And you notice the 10 biggest ones, they all had flood levels between about 9 and 10.5 feet. 10.5 feet is where you get water into the New York City subway system. Now, New York City subway system is the lifeblood of the city. If that shuts down, the city shuts down. If it shuts down permanently, I don't know what happens. The only storm here that breached the subway system was Sandy by a whopping 3.5 or 4 feet. Luckily, and also not just luck, but due to the hard work of the subway crews and the other emergency workers who worked very hard day and night. They got the water out of the system fast, and because the signal systems are made of, they're old, they're irreplaceable, you'd have to rewire the system entirely if those signals corroded. You couldn't buy them off the shelf. The subway was able to come back in 3 or 4 days. But what's remarkable to me here is it almost flooded 9 other times. And you know how much the city, well actually I'm blaming the city, it's not just the city, it's the, what's now called the MTA. It was the city back here and it got transferred to a state authority. What they did to protect the system, 0. So you want to ask yourself, you know, with all those near misses, what were they thinking? Why didn't they, for instance, do something about the ventilation systems? If you walk the streets of New York City, you know, they have these gratings. Well, the water goes right down the gratings. The subway entrances are right at street level. The water goes right down the steps. You know, they did nothing to defend against that free access that water has to the system. Now, they're finally starting to develop a new ventilation system, and they're talking, although I don't see any doing, about having a system for plugging the tunnels when a storm like this is imminent. And they're raising some of the entrances above street level. But, you know, it took 9 storms before they got the message, and the system had a flood once. If you look at the rest of the problem, all the rest of the issues with siting, with infrastructure, with emergency rescue, they all look the same. You have to take a punch, and take a punch, and take a punch again before the political system is responsive. So it's a fight. Basically, it's not so much about a more accurate calculation of what the ice sheets are going to do. More than that, it's about getting smarter about getting the political system to respond. And again, this is about the risk as it was, you know, this is 65 years ago. Sea level's gone up since then. The risk has only gotten worse. So let's talk about some of the fixes. The system isn't, political system, the management system isn't completely dumb. We have done some things, as I said. So in New York, one of the most obvious things was that the hospitals, many of them sat right along the estuary here. And hospitals have emergency equipment because they have to, because the electricity does go out. There's a blackout every 10 or 15 years. What they didn't realize is they shouldn't put the emergency generators and the fuel in the basement, because they weren't thinking about the flooding capability. They were thinking about a blackout happening somewhere else. And so, okay, so they learned from this. It cost $1 billion to get one of these hospitals back on its feet. And what they did is they now require all the hospitals that are along the coast to move the emergency equipment and the fuels and all the other systems up above basement level. And in the city code, it now requires that new hospitals be sited not here, but in the middle. It's good. That's progress. It was facilitated by the fact that the hospitals are, you know, those are private entities, and the public doesn't, except in the rare case of Bellevue Hospital over here, the public doesn't have to pay for it. Much easier for politicians to make decisions. I should have had this slide another place. A friend of mine was trapped in 1992. The Hoboken subway station over in New Jersey was flooded, and he was down here, and he ran for his life. And I remember him telling me the story, very vivid, even though he's like, talks in a monotone. Could be a jet pilot, but you know, so discounting for the fact that he doesn't get excited, it was an exciting story. But here's 2012 during Hurricane Sandy in the same damn station. They did nothing to protect the station. Okay, so that leads me to want to talk for the remainder about this question of what can be done and how we can improve governmental responses and our responses, frankly. There are lots of, you know, political and psychological obstacles to doing the right thing. As I said, memories are short. The episodes are infrequent. They don't happen very often. So if you're a politician, your returns on investing in adapting and building resilience are very low, because The next Sandy might come, even with global warming, it might not come for 20 years, in which case, you know, you're going to raise people's taxes to build something that is going to be useful after you're out of office by 15 years. You know, I don't have to tell you about how likely that is. It happens sometimes, but, you know, there's a headwind against doing the right thing. The investment doesn't produce in the time frame that the people making the investment want to see it. And in fact, some of these investments are for 30, 40 years down the line. And to be cynical about it, it's hard. That's hard to get leaders to make those investments. Not unheard of, and I'll get back to that in a minute. The planning times are long. The Thames has a surge barrier. That means when there's a big storm coming along out on the North Sea that's going to raise sea level and push water up the Thames estuary, they bring the barrier up from the bed of the Thames, and it protects London. The reason they did that was because there was a big flood in 1953 that killed several hundred people in the London area. Same storm in the Netherlands killed several thousands, despite how good they have been historically, because during the war they let things slide. And that caused both the Netherlands to buff up its coastal defenses, but it also caused the UK to build a Thames surge barrier, which has worked quite nicely since then. But between the time the flood happened and the planning started, and then making the plans, getting political agreement, raising the capital, pouring some concrete, it's 30 years. So if we start on some of dealing with sea level rise requires mega projects. If you're going to do that, you have to start planning way, way in advance, and you have to plan not for today's risk, but for risk in future decades. That requires a level of sophistication, a level of forethought, but it's not unheard of. We build water supply systems, we build highway systems, we build sewage systems. All these big infrastructure projects require building for the next generation, essentially, especially water supply. And yet we have done it, we will continue to do it. It just has to be passed on to coastal defense, because the risk is only going to be increasing. Another problem is that the governance structures are complicated and not well aligned with making these kinds of decisions. In the UK, there's a very vertical governance structure. It's easy to make a decision. There's one or two entities involved. You try to make a decision like that in the state of Rhode Island or the state of New York. There are multiple overlapping jurisdictions. Different interest groups have their fingers into each of the different jurisdictions, and actually getting decisions made about big projects is very, very difficult. So it's part of the beauty of our federal system is that it's not possible. It makes it harder to get bad things done, but it also makes it harder to get good things done. And finally, and perhaps most importantly, the political incentives are all in the wrong direction. Not only are political leaders being asked with this problem to do something for the future rather than for next week, but if you think about a decision maker here we have a decision maker who's tasked with making decisions or informing decisions about a big project. And they can either build resilience, build infrastructure, or either hard or soft, like improving wetlands, which will defend against the coast and make tough decisions on zoning and so forth, for which they get usually, except briefly in the wake of Hurricane Sandy, zero money from the federal government, versus wait until after the disaster, in which case the federal government opens up the coffers and spends, in the case of Hurricane Sandy, $80 billion to help communities clean up the mess. Now, I'm all in favor of spending the $80 billion, but if we had spent a little bit beforehand, the ratio was argued about, we could have avoided a lot of the $80 billion afterwards. But if you're a decision maker, even if you have the best of intentions, there's a big thumb on the scale that says, don't do that, you won't get reelected. Wait and let the federal government clean up afterwards. It's probably more subconscious than conscious, I don't know, but it's there. So, let's see. Okay. So there are the problems, multiple overlapping jurisdictions. Politics as usual makes this stuff hard to do, even though we've done it with some infrastructure. By the way, I use the subway tunnel case here. New York City doesn't have control over the subway, so it's a state it has to go to plug the subway tunnels, essentially. So again, that's an example of differential jurisdictions. The federal policies with the skewed incentives, particularly under the National Flood Insurance Program. The Stafford Act is the federal regime which comes in and pays afterwards for cleanup. And the private insurance system doesn't play in flood insurance anymore. That's why there is a federal flood insurance program. And there are multiple threats from climate change. Some of them, the private insurance system is very much there still. And that system is not operating very well either for various reasons, but I don't have time to go into it. So, all right, so New York City is moving along. They are doing certain things. What they're not doing is, and by the way, these are northern Jersey where you can see some of this happen. This is happening around here too, right? We're over there raising houses. This is, straightforward, sensible decisions. Really, these big cities, Boston, New York, are faced with, are we going to do this, which is this is the evacuation of patients from those hospitals where the emergency equipment was flooded out. That, as I showed you, is something we can address. But if sea level rise is high enough, we have to do something like this. This is the Thames surge barrier. And we're not engaged in that conversation at all. We're not engaged with this, and we're not engaged with the question of how much we're going to have to retreat eventually, which we will have to do in certain cases. So you have a choice. We have to make smarter decisions about the kind of infrastructure you build. We can't bulkhead or breakwater our way out of this problem. It's too complicated and expensive. We need a more subtle set of coastal defenses, which involve, hopefully, a lot of nature-based defenses, like reefs, even artificial reefs, enhancing barrier islands, dunes, and very important, particularly on the Gulf Coast, has been re-enhancing the wetlands. But other things like making surfaces in cities more permeable are going to be extremely important. These are all things that, as I understand, are being talked about here. And this is a plan that group at Princeton that I work with developed for the barrier islands off New Jersey. You can see in some of these areas, some of them you put everything up on stilts, and others you let the communities be floodable. You replace streets with canals, basically, and you give places for the water to drain. They do this in Florida for entertainment. We might have to do it up here for storm protection. That's the kind of thinking we need. So let's see, this is all stuff I've already covered. And most important is a new relationship between the federal government and the local governments, because the federal government has immense resources and power. The local governments have small resources and very restricted power. And when the federal government has this immense leverage, as it does with the federal flood insurance program, it has to use that correctly. And right now it's not. Not only are the incentives screwed up, when the program was originally thought of, there was supposed to be a big pot of money to build resilience in advance, and it just never was filled with money. But also the maps that FEMA puts out for the 100-year flood lines, which determine who needs to get flood insurance or not to be able to build, the maps are wrong. They're wrong in the first instance because they don't take account of sea level rise. And they're wrong because they have certain mistakes in them, details I'm not going to go into. But the feds just have to get their act straight, or else this is never going to work. And I'm done, actually, I just realized. So, the bottom line, I got so into it, I didn't realize. The bottom, right? Thank you. So, the bottom line is that, we got a big problem. It's only going to get worse if we sit on our hands. That we have certain experiences with thinking ahead, which have turned out to work quite well. Coming from New York City, my prize example is the New York City water supply system. They're building the third water tunnel. You may have read this, because the other two tunnels are 100 years old. They're going to collapse. They're already leaking. They need another water tunnel to be able to shut down one of the others and go through it and fix the leaks on the old tunnel. They've been building this thing since 1970. Through financial crisis, through recession, through the great recession we had a few years ago. But the point is they kept building it. They knew they needed it. They kept doing it. It became like the subway system. You just keep doing it because without it, the lifeblood of the city dies. That's the kind of forethought we need. It's the kind of planning we need. We will not get away with not doing it in this case. It just won't work. So, you know, what I see from spending a day here, what I see from dealing with the leaders in New York as a technical advisor, is the potential is there to really do it. There are a lot of very thoughtful people, particularly at the technical level. There are some political leaders who know what the right thing to do is, but they're not going to do it unless they get support from us, basically. And that's the bottom line. Thank you.
We have quite a bit of time for questions, and I'm going to pass the microphone around so that it gets put up on the live cast. So question over here. And he is mic'd, so he can, we don't have to pass the mic back and forth. All right. Here you go.
There's a paper in Nature about a month ago by DeCanto and Pollard where the numbers are about double for 2,100, 5 or 6 feet of sea level rise and a 50-foot rise in 500 years. And also the Andrill holes in Ross Sea and Antarctica show that during the Pliocene at today's CO2 level, the sea level was 20 meters higher than today, plus or minus 10. And then they know a lot more about the bottom of the Antarctic ice sheet than you represented. There's a lot of other things going on that can cause a collapse of marine-based ice. And there's about 17 meters of marine-based ice in East and West Antarctica, and there's special things about the deepening of the rock as you go towards the middle of the continent that cause it to be unstable.
Before deep in bed, it causes the instability, yes.
So, but what you were presenting wasn't that.
No, that's what I said. I said that the ice in West Antarctica is unstable, and some of the ice around the fringe of East might be unstable.
Well, the recent work, I go to Antarctic meetings.
So what's the question?
Well, I'm just pointing out some stuff that I thought you were inaccurate on those things. There's about 3 meters in West Antarctica. The other 14 meters are in East Antarctica. So there's large basins like Wilkes Basin and so on and so forth that are susceptible to collapse. And there were papers in 2014 saying that they were no longer buttressed and they are collapsing.
Yeah. Okay. So much of what you say is right. I didn't want to go into all those details. As I said, the 20-meter number from the Pliocene is consistent with what I said. What we don't know is how fast it happened. The Pliocene was millions of years ago. We don't have a good way to measure the rate at which it happened. The last interglacial, there was, as I said, it's a lower number, 5 to 10 meters. We also don't have a good way to measure the rate at which the ice was lost. And that's the key thing. Nobody doubts that if you leave a warming of 2 to 3 or 4 degrees on the ice sheet long enough, and it's actually higher down there, that if we have a global warming of 2 to 4 degrees, we're going to lose that ice. There's no question. But from a societal point of view, the key question to me is how fast is it going to happen, and how much is going to happen faster than we have the ability with our current disposition to respond. Go ahead. Oh, well, you start with the DeCanto and Pollard paper. Let me just answer that because I think it's an important point. So one of the daunting things about this problem is that the science changes all the time. And if you're asking decision makers to make plans and make decisions based on information which is different 1 month than the next in some cases, it's very hard for them to do that. And one of the difficulties we have in the scientific community is properly framing things. So for instance, those are really good scientists, and they made an interesting discovery by introducing 2 new processes in their model which had not been paid proper focus before. But the model itself is still imperfect. There is no perfect ice sheet model, and we need improvements across a variety of fronts. So, you know, how you incorporate the idea that their estimate is twice as high as the previous one, I wouldn't want to see all decision makers all of a sudden jump to assuming that that's the final and right answer. It isn't. We need a more subtle way to incorporate it. And Pollard and DeCanto say that themselves. And they didn't misrepresent anything. It's a good paper. But next week, there could be a paper showing the number slides back in the other direction. We need a way to better represent the probabilities to decision makers so they aren't faced with this sort of ping pong back and forth, which is what they've been getting. So I don't basically disagree with anything you're saying. I just think no discovery at any one time reframes the universe with a problem that's this complicated.
Two questions related. This may be a layman's version of the same question that was just asked, but I understand that Hansen and Company have recently done a study that said that we can, based on the historic data, they find that this flipping, which you demonstrated on a graph up here, can happen much faster than had been predicted. And I wonder, what the current status of that is, what the thinking on that is, because I think that in terms of moving people, when you're talking thousands of years, it doesn't really grab folks. Related to that, I always ask Grover whenever I'm at a meeting with him, what's the projected sea level rise this month? And I was under the impression here on the coast that NOAA was saying now it could be in the party situation, okay, that NOAA was saying 7 feet. He's suggesting only 3. Could you guys clarify that?
The 3 meters is the 3 feet is the IPCC projection from 2013. Papers since then, including one that I wrote and some of these other papers, suggest it's higher. And the recommendation that NOAA makes is to use basically 2 meters or something 6.5 feet as a sort of worst case. Whether decision makers want to use a worst case or not, they're not necessarily going to do that. Depends on what the cost and implications are going to be. But that's what that recommendation is. And it's not far from what the latest, we wrote a paper. I showed you the numbers for New York City and Newport were about 1.5 meters, which is getting up around something close to 5 feet. So these numbers are all drifted up in the higher direction. Whether that drift is, I can't predict what science will do. We could come back in a year from now and they could have drifted back the other way due to other discoveries. We don't know. As far as the Hansen paper is concerned, it goes to the point I was trying to make to this gentleman here. We're going to get, papers are going to come and go like that, and they were taken together. That's how science progresses. The Hansen paper has a rate of sea level rise for this century which goes as high as not 2 meters, but 5 meters. Much higher than my estimates, much higher than you would infer from DeCanto and Pollard. So, in my view, and in the view of many of my colleagues, what the Hansen paper has is like a worst case. It's not impossible, but they've taken the worst case outcome from several different lines of evidence and combined them, concatenated them, to have an estimate, which is really a scenario of what's the worst you could imagine the thing getting. You have to ask yourself, is that something, how useful is that for decision making? I don't know how to answer that question myself because I don't make decisions, and you should probably be happy about it that I don't make these decisions. But I can tell you it's difficult for decision makers to deal with worst cases. What they prefer to deal with mostly are probabilities. And the scientific community has been trying to present these things probabilistically. So what you'll see as you move towards the next set of assessments, which is starting to happen now, is information like Hansen's, like DeCanto and Pollard, will be integrated. Experts will look at them and make some assessment of how all the evidence fits together and present to decision makers some kind of set of probabilities. Yes, this thing Hansen could happen, but I'll make up a number here. It has nothing to do with what I would actually judge today. It might have a 1 in 1,000 chance. I don't have a number in my head, but say that's what they'd say. The DeCanto and Pollard outcome might have a 2 in 20 chance, or maybe more. I don't know. But that will require thorough analysis of all the studies that have come previously and will come in the future. No one study is ever the final answer. They're all informative, none are conclusive.
Thank you. Question up here.
Yeah, when you talk, and again, time is everything. Things are increasing. We all know sea level rise is actually occurring. The rate of change is, of course, at least by all rights, quite great. A couple of things. One is it a linear relationship, you believe? What's happening now and what may happen in the year 2100? Or will there be a spike at some point? Maybe,
Well, it's
sea
not
level
linear.
rise.
It's, the rate
I mean, that
been
may help planning in the future,
Okay,
or
so-
right now for the future.
Yeah, so the rate has been accelerating. That means it's not linear.
Yeah.
Many of these processes are known to be not linear. One of the reasons is that the ice sheet contribution has become larger in recent decades, and that contribution itself is known to not operate in a linear fashion. So if you go down to Antarctica and you measure the rate at which icebergs are forming and streaming off the continent, it's a process that's been accelerating. So one of the issues is, does it reach a point where some part of the ice sheet actually just collapses out and out? And it's one of the things we are not sure about because of the modeling limitations. So
We could see a straight line between now and the year 2100 in terms of sea level rise, or it could be
it curves up. It's not straight. It
Could be.
curves up.
And one more question. FEMA, you're not the only one. Everybody, I've seen it too. What do we do? There are so many important decisions based on the FEMA maps. And you admitted that you see a lot of faults in them too.
I don't have a good answer for FEMA. All I can tell you is the more people complain about it, the more likely, and you have a senator here, you have a couple of senators here, one of which is deeply involved in this issue, White House. Another of which has a lower public profile, but is a very effective guy. You have representatives in Congress. They ought to hear your voice on this. That's how things change. Or, if they don't do what you want, so elect somebody else. But it doesn't do any good to go home and, bitch about FEMA. Nobody's going to hear you. You have to complain to the right person.
Yes. What part does evaporation have in reduce the level of sea level rise? Or does it have any factor?
Sure. I mean, the water system of the Earth maintains a balance. And part of that balance is water evaporating from the ocean. But what goes up comes down. So, yeah, it comes down different spots. It comes down on an ice sheet. It builds the ice sheet. So, in fact, in the warming world, one would generally expect more precipitation to be occurring, particularly in what are now the colder parts of the world. So the projection is that we're going to get more ice accumulation on Antarctica and Greenland in the middle. The trouble is the rate of loss at the edges is, for now at least, has exceeded the rate of increase of gain in the middle. And so it's part of this great cycle. Unfortunately, the cycle is running in a way which yields, a net gain of water to the ocean. And that's causing about a third of the current sea level rise is due to loss of ice from the ice sheets. All right.
Question here in the middle.
My question is, can you point us to some jurisdictions, either in the States or around the world, that are incorporating this information effectively into their capital investments on different timescales?
So in the U.S., you've got several jurisdictions which are looking at this seriously, but they're not at the level of making policy on a comprehensive basis or creating a set of incentives. Rhode Island isn't far behind, if behind anywhere in the U.S. So you've got planning processes in the Los Angeles basin, in Boston, in the Miami area. State of Delaware, I know, has one. There's a more rudimentary process going on in New Jersey. And the New York City is probably, from a technical point of view, where the cutting edge is, although you guys are up there also. But none of these areas have turned it into effective policy, with the possible exception of New York, and only because it got smacked hard by Hurricane Sandy. So there was a need to actually implement some policies. I think other jurisdictions think they have more time. So internationally, the Dutch have always been at the cutting edge on this, and they're making a lot of money now, by the way, with their consultants coming over here and advising places like, New York. So, but there's a lot of very bad coastal development that's still going on nearly any place you want to look. There is, by the way, Shanghai, which has had traditionally a really bad relationship with the ocean, is starting to do some intelligent planning as well.
Question over here.
Do you have any comment to make about the level of discussion at the presidential candidate level on this subject?
That speaks for itself. I mean, on the Democratic side, there hasn't been much discussion because although they disagree in detail, they don't disagree about the need to deal with this. On the Republican side, they don't disagree. There hasn't been much discussion because they don't disagree either, as far as I can tell. They just basically don't believe in the problem. Now, what would actually happen if one or the other side were, one or the other is going to get into office? I don't know if a Democrat got into office, if they would have the political courage, essentially, to do what needs to be done. Many have tried and not tried. That we've had 25, 30 years of there being enough information to deal with the problem where not much has happened. So I don't know. President Obama has done a very good job. He's done as much as you could do without the Congress being involved, is basically what's happened, using regulatory authority that the Supreme Court gave him with a 2007 decision. What would happen, I think, speaking my own personal view, not as a scientist, I think Donald Trump is unpredictable. I honestly don't know what he would do if he were president. I don't understand what goes on in his head. And so I don't know. If he got elected, I would want to go talk to him and convince him this is an important problem. And I don't think he's necessarily unconvincible. Ted Cruz has been very firm in illustrating a significant level of disbelief about the problem. And him, I think I know more about what I tend to take him at his word more than I take Mr. Trump at his word. So that's why, as an American voter, that's what I make of it. Not as a scientist. Separate question. And by the way, what I know about that isn't much better than what you, if at all, than what you know about it. So you should be followed by your own instincts, not by mine.
Question here in the middle.
Well, first off, thank you very much for your talk. You've been involved in the IPCC for many rounds, and that's pretty much the gold standard in terms of understanding this issue across the globe. My perspective is formed by what I read here locally, and I don't have a good sense for how this is being perceived across the world. Can you give us a summary of how you think this issue has developed, how public understanding has developed across the globe, and most importantly, the world's willingness to deal with this issue in some meaningful way?
So in Europe, for reasons that are not entirely understood, there's been a consensus that this is a big problem that this meaning climate change in general, is a big problem, needs to be dealt with. And politicians don't publicly cross that consensus. They support it. In fact, part of the reason I think the consensus became so strong is when it started to develop, political leaders took it as to their advantage to try to support this approach, and so it sort of fed back on itself. And I think the triggering event was in 1986, a long time ago. The German Green Party won enough seats in the parliamentary election that the two main parties in Germany proceeded to co-opt them. And ever since that happened, the EU, which didn't exist in that form at that point, the position of eventually the UK changed its position because of Margaret Thatcher took it as a serious issue. And this core coalesced centering on Germany where there was strong European support for the issue. That level of domestic support has never existed in this country. And part of the reason is that not only has there not been the political leadership until recently, but I was as chief scientist of the Environmental Defense Fund for a long time, so I take partial responsibility for this. No one was able to identify an effective route for political grassroots organization on the issue. So a lot of things weren't tried that probably should have been tried going back decades. And we still get to the point in the United States where, although public opinion relatively strongly supports action on the issue, it's relatively shallow, and it switches quickly depending on who the leader is. So for instance, after the Kyoto Protocol was killed in 1967, several polls were taken, and it had fairly good public support on both the Republican and the Democratic side. After George W. Bush became president and took the U.S. out of the Kyoto Protocol, the next set of polls had a big split, where Republicans drifted from support to opposition and Democrats drifted from strong support to stronger support. It became a symptom of the polarization in American politics. So what you're really asking is, in the current polarized atmosphere, how do you get people to think about wanting to grapple with a problem that's this big and needs some really comprehensive approach? And the only solution I can think of is political leadership that wants to grapple with the problem. That the only progress we made was in the last 9 years, particularly since the Obama's second term, where he just made a decision that the issue was part of his legacy and this is what he was going to do. Why he made that decision, how he made it, I can guess, but I really don't know. But that's what it takes. So if the next president becomes convinced that this is, or is already convinced that this is a critical issue, you will see progress on it. If not, you will see backsliding, and then the chances that the world avoids the party scenario start to look awfully bleak. Because the U.S., in spite of not being the world's bigger emitter anymore, China is, our emissions are going down, is the most important political actor still on this issue.
Thank you. Question here.
I was really interested by your first bullet point there, and just wanted to ask a little bit about what's necessary to have the Army Corps of Engineers evolve and the engineering trade as a whole evolve. And do you have examples of that where you've seen it maybe globally, where there's a bit of a change of mindset where you can get away from, design times 3 and it works, or hardened structures and more of this, as you said, like kind of a migrating to a mix of hard and soft? What do we need to do what do we need to do locally here in Rhode Island and also, in the States to get that evolution to occur?
So the Corps is not impervious to criticism, and the Corps, I don't know exactly how it happened, but in the wake of, since Hurricane Sandy, probably because of the huge amount of expense that the whole thing represents, and probably because they know they're going to get a lot of money anyway, has been at least talking about a softer approach to some aspect of coastal defense. So they've spent a fair amount of staff time investigating what they might do in certain cases, like the Louisiana situation, to not depend totally on pouring concrete. And they've been receptive to at least listening to these ideas. Now, how that'll affect policy when it comes down to some congressman or woman saying that they want a big infrastructure project in their district because they want the jobs, and it becomes a matter of congressional appropriations, I really don't know. But I will say, for the first time since I've been paying any attention to the Corps, which is some decades now, they do actually seem to be listening. There's a gap between listen and act, and I don't want to make any claims about what I think they're going to do in the future. But people who are usually very skeptical about the Corps, including my friend who ran from being drowned in the Hoboken subway station, who's worked on this for 40 years, not on this problem, but on coastal issues, not on this climate change problem. These people are marginally more optimistic about being able to change them. And it comes down to just like everything else. These are political decisions. They are not primarily driven by good science or good engineering. They're driven by the other stuff that goes into these decisions. And so they have to be engaged as political decisions, at least partly. You got to get the facts right, but that only gets you about 10% of the way you want to go.
Question in the back.
This came from one of our home viewers through text. How do we create a better resolve for policymakers to look at climate change in a comprehensive manner rather than piecemeal?
Well, it's hard, and maybe not, actually, at this time, it might be not the right way to go, oddly. We've been trying, comprehensive solutions to the problem were tried. That's what the Kyoto Protocol represented, for instance, and didn't work, partly because it was trying to bite off too much at once, and a lot of countries, particularly at that time, the big developing countries like China, weren't ready to do what probably they should have started thinking about doing. Also, the US tried a completely comprehensive approach by the cap and trade legislation that the so-called Waxman-Markey bill that passed the House in 2009 and failed in the Senate the next year. So the mood around both the international and the domestic scene is, let's try to break it up into pieces which might be politically more manageable. So you see the development at the international level with the Paris Agreement really being not about a comprehensive solution, but about individual countries coming and talking about, this is what I think I can do over the next 10 years. This is the level of effort that I can get done in my country. That's what the leaders are being asked to do. And that's the framework of moving forward for the next 10 years, at least, I would say. Domestically, the regulatory program that that EPA has proposed is basically a bunch of individual pieces, some of them pretty big, like the improved CAFE standards, the power plant regulations, new plants, existing plants, and piecing those together in lieu of a comprehensive national program, which the Congress isn't going to pass. So I think more important than worrying about being comprehensive at this point is showing that even in situations where political progress is impossible, that progress on the substance of the problem is possible. So, and there are more detailed arguments about how to do that at the international level. I'll give you another example. There's a group, an organization under the UN called the International Civil Aviation Organization. They control everything about international aviation under the Chicago Treaty, it's called, of 1944. It's a very strong treaty. And under that treaty, they can punish countries who don't comply by preventing them from flying in the airspace of any country that does comply. There's nothing like that in the climate world. They were given the job by the Kyoto negotiators, because the Kyoto negotiators couldn't figure out how to handle it, about dealing with aviation emissions. And after stalling and stalling for complicated reasons, they finally decided to deal with aviation emissions. And they've set a weak but a first standard, and they're moving on to set another set of standards now. And it's a small sector of the global emissions profile. It's about 3% of CO2, but it's supposed to grow twice as fast as everything else taken together. So it's an important segment. You might say it's a small piece, but if you found a bunch of pieces like that, especially in treaties which have good enforcement mechanisms, then you might actually make progress. There's another piece like that, what's called the Montreal Protocol, which was designed to protect the ozone layer, which eliminated the freons, which were themselves potent greenhouse gases, substituted other gases, which are also potent greenhouse gases, called hydrofluorocarbons, to do the coolant, serve the coolant functions that the freons previously did. That treaty is now being used, it looks like, it's planned, to control the hydrofluorocarbons, because they are themselves potent greenhouse gases. The Montreal Protocol has vicious enforcement provisions. You can slap trade sanctions on any country that doesn't obey the treaty. And there are other agreements like that lying around. So while we're having trouble getting countries to agree to binding limits through a Paris-type accord, we should be also pursuing all these other routes. It will take many different types of efforts.
Thank you. Last question here in the middle.
Thanks. So I think you've painted too complicated a picture of the politics, so I'd just like to ask a science question. If you had like $1 billion, like the cost of one berm in New Jersey perhaps, to allocate to a science initiative that would reduce the uncertainties in the forecasts of sea level rise and temperature after 2050, where would you spend it?
Well, my immediate answer is I'd spend it resolving the ice sheet question because it's something I work on. Even if I don't get the $1 billion, I think it's a worthy problem. But the real answer is I wouldn't spend $1 billion on any one thing. I'd break it up into 3 or 4 things. One of the areas that ice sheets are one area that is critical and where progress has started to happen. I think that's important. Another area that's really critical where progress has started to happen are small-scale models that can describe phenomena at a scale of, say, a hurricane. We're starting to finally make progress at that level, the high-resolution level. And I think that that's worth a significant investment at this time. But I also think that there's a whole set of questions that aren't physical science, but that are social science that we've slighted and that need to be investigated if we're ever going to understand the human side of this. What gets people to want to react to this kind of information? What's the best way to transmit the information? And what makes it easier for decision makers to actually make decisions which reflect risks coming forward? So the whole area of risk management in all its ugliness, running from decision making down to, or from the individual psychology of how people think about these problems, to how decision makers mobilize people to actually get behind the decisions they want to make. That whole area is worth a lot more than it gets right now. Thank you. Thank you.
So, thank you. That will conclude tonight's speech. But I think you see why we were indeed fortunate. Michael's knowledge on this subject and frankness and bringing it down to a very understandable level, I think is unparalleled in terms of the explanations that we've gotten in the past. So thank you, Michael.